All right, well, I think it's really great that you have this theory component. In fact, it's essential. You really should not ever consider going without in the future. And hopefully my idea is that I'm also going to try to explain why. So actually, Darrell gave a very good lead into the idea that theory is an important part of the education for people interested in quantum materials by Xing out the rule, don't talk to theorists, and also in addition. David Mandras yesterday mentioned a bunch of papers, and so just to kind of give you a sense of how closely theory is tied into every aspect of work on quantum materials, I went and looked at a few of the papers that he mentioned, like the MOS2 paper. In every paper that he mentioned, you can find, if you're looking for it, some reference to theoretical calculations, or a theoretical collaborator who actually did stuff that's presented as part of the paper. So here they refer to earlier ab initio calculations about the band structure. Here they both refer to theoretical predictions of how to improve mobility, which they drew on in their work, as well as suggesting further theoretical work. And in the van der Waals magnets, here's an actual theorist collaborator who did the first principles calculations to show spin lattice coupling in these van der Waals magnets. And in this paper too, there's theory kind of throughout, so I couldn't just cut and paste it for you because there was a lot. So that's just, again, this is just to kind of give you a sense of a motivation for why you should understand a little bit about what kinds of theory is being done here. And also in my own group, we generally work in experimental theoretical collaborations. And a lot of times it's the postdocs and students who are talking directly to each other. So if you work with us, you might be talking directly to a theoretical postdoc, collaborating to get the work done. So I guess also I want to get the important messages of my talk in at the beginning while everyone's still paying attention. And again, I'll develop these ideas. So this one, I've already kind of given you some quick evidence for the fact that it might be true that we can get really useful information about the structures and properties of solids, and that it's actually, we'll see in some ways, it's complementary to what you get from experiments, which is one reason why this combination is so powerful. I also want to put in a little warning, which I started putting in when I gave earlier versions of this talk, and now is evolving. So we have first principle software, which you could, in principle, use to do calculations yourself. And I'll mention a little bit more about the newest development, where you can just look up first principles calculations in databases. You don't have to learn how to use the software. But in any case, you do need to be careful when you use results from first principles, doing the calculations correctly, as well as interpreting the results is not always as simple as you might think. And so again, without, in this hour, I'm going to try to give you a little sense of how that is, but, hopefully without killing your interest in using theory, but, understanding how to use it correctly. Okay, so this is what exactly are these first principles calculations? Well, they're really, studying solids from first principles, from the laws of quantum mechanics. So we learned, back in the 30s that solids are described by quantum mechanics. They're just interacting electrons and nuclei. And there's the famous quote from Dirac, and I'm sorry if you've heard me, or other people use this before. It's very common. There's a quote where Dirac says, "The underlying physical laws necessary for a mathematical theory of a large part of physics and the whole of chemistry are thus completely known." And that's true, and is often used to denigrate solid-state physics as a kind of inferior branch of fundamental physics. But in fact, I don't even think that was Dirac's intention necessarily, because there's a longer, the quote goes on, says the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. And of course, that the meaning of that last phrase has changed a lot in the last 80 years, but we'll talk about that as well. So let's, just quickly, the quantum mechanics, you all know, the Schrodinger equation for 10 to the 23rd particles. The Hamiltonian for the interacting electrons and nuclei has kinetic energy terms for the nuclei and electrons, and then Coulomb interaction terms. The Hamiltonian itself is very simple. And then the first step is the adiabatic approximation, where we break the Hamiltonian into two. We sort of break this down into two steps. We have an electron system with electron kinetic energy and interaction terms, and then a nuclear Hamiltonian where the nuclei move in a kind of effective potential given by finding the ground state energy for the electrons in the potential of the fixed nuclei at given R. So the first part of the talk, I'm going to say, suppose we know what this ground state energy is, what this effective potential is for the system of the nuclei. What could we do with that? And then I'll go on to give you a kind of a glimpse under the hood or into the black box, to mix metaphors, of how, where this function actually comes from. So let's first suppose that we have a way of obtaining this function so we can focus just on the nuclei and how they're interacting. What can we do with that information? Well, the most obvious thing you can do is structure determination. So if I have ions moving in an interatomic potential, then the ground state structure, if I treat them, since I'm generally going to treat the ions classically, would just be to minimize the energy with respect to the ionic positions. So if I have a diatomic molecule, I have one parameter, the interatomic separation. I have this E naught, this should be E naught, plotted as a function of R, and that's the predicted interatomic spacing. All right, this curvature will also gives me more information. It'll tell me the vibration frequency for this mode. So these are the types of quantities I can predict from this E naught, and it's not just for molecules, it's also for crystals. So here I have a little, say I had a little two-dimensional infinite lattice. I have a single parameter, which is the interatomic spacing. If I can compute E naught as a function of this parameter and plot it out here, this is obviously schematic, then I can predict the interatomic spacing for this simple crystal. And that, of course, then goes on. I could say, well, suppose that I have some element and I want to know, is it going to form, what's the crystal structure going to be? Well, what if it's not square? What if it's something else? So then I would be able to say, let's suppose maybe it's in a triangular lattice. I'll compute the energy of the triangular lattice with respect to A, minimize it, and then compare the two energies. So whichever's lower will tell me which one is, I'm predicting as the structure for this particular material. And, of course, I might have to consider other structure types as well, but, you get the, that's the way first principle structure prediction works. And then just to, in case you were wondering, there's really no problem in going to more than one atom per unit cell or to 3 dimensions. It's just a question of parametrizing the structure. So this is something that's very natural in crystallographic framework. You have a unit cell, you have a space group, you populate Vyckoff positions, you get a set of free parameters, and then you can compute the energy as a function of the free parameters to predict the structure and the energy, the lowest energy you can get in that space group, in that structure type. And again, that gives you the predictions. So just to, again, give a very kind of classic example of structure prediction in a fairly interesting system, we have the perovskite oxides. This I don't have to explain, right? Everyone's good there. And if I'm interested in, say, barium titanate and strontium titanate. So I'm going to do the calculations to predict the structure for barium titanate and strontium titanate, looking at this structure type. And with 5 atoms per unit cell, I have 5 structural parameters, Ca, and then possible displacements of the atoms along the z direction, and that will all keep me in P4 space group. All right, and then if I take my black box and compute the energy and do the operations that I just explained to you, then for barium titanate, I find that the P4 polar structure is stable. I get a lattice parameter, an A lattice parameter that's a little less than 2% off from experiment, and pretty good internal atomic parameters. So this is computed, this is experiment. And for strontium titanate, I'll get that it's paraelectric. It doesn't want to deform. And again, I'm off by about 1% in terms of lattice parameters. So this just gives you a kind of flavor of, what these compounds look like in what I would call first principles world, okay? Where, you can also, I mentioned you can compute vibrational modes. In crystals, you can compute phonon frequencies and eigenvectors. And so just this is, wanting to impress you with a kind of complete comparison. I'm going to go back to gallium arsenide in 1991. The lines are the first principles calculation, and the dots are experiments. All right, that's, I hope you're impressed. I'm impressed. A more recent example is work that we did in my group on spin phonon coupling and strontium manganite, which is a magnetic perovskite. We were actually looking at epitaxial strain and the effect on the phase diagram. But in the course of that, we came up with a sort of what for us was a startling observation, which had not been previously discussed. And so I wanted to present this as a first principles prediction, where we are predicting something that was not observed before. We found it, as opposed to, say, the lattice parameters of barium titanate, which people would actually come up to me at conferences and say, have you actually ever predicted anything that wasn't already known? Like, well, yeah, well, that, like in 1995, I'm like, well, no. I mean, like, I'm happy I can, even get within 2%. Okay, so. Right, but we're in the last 20 years, since about 2000, we've moved into a mode where we're in first principles world, we're doing exploratory stuff and sometimes finding things before the experimentalists have gotten there, and that's fun. So here, what's going on here is we computed the phonon frequencies for this perovskite, at a few high symmetry points, and noticed that if we put the spins in the antiferromagnetic order versus putting them all lined up, the phonon frequencies were hugely different. So this is 121 wave numbers. This I means it's unstable. Okay, so this is a large effect, and this is usually spin lattice coupling isn't really that big. So I was going around talking about this, and then so we do have an experiment. You can ask, well, how would you see this experimentally? And one way that we came up with was to look at the paramagnetic paramagnetic antiferromagnetic phase transition. So when the system itself goes from being paramagnetic to ferromagnetic, it's changing the magnetic order. And so you can look and see what happens to the phonons as you go through the transition. And so Stanislav Kamba in the Czech Republic, who was interested in studying these systems, looked for this shift, and it's like over 30 wave numbers through the transition, which anybody who knows would know this is a huge shift. And we did a very, very crude model with Heisenberg, Hamiltonian to try to predict this from theory, and that, it actually came out surprisingly well. So, we were pretty excited about that. And I'm trying to use this word de novo predictions for predictions that are not postdictions, but truly predictions. All right, so this gives you a little bit of the flavor of what you can do with first principles calculations. I've focused on the things in blue. I'm going to talk. We can also, as you'll see in the next section, we generate information about electronic states, and also information about the electric polarization of the system. And with that, we can expand the kinds of properties that we look at to optical and transport properties and polarization-related responses. Everything we do is in periodic boundary conditions, and the smaller the unit cell, the better. The computational effort scales as you make the unit cell larger. So, we're very good at perfectly ordered crystals, which are hard to see experimentally. So in some sense, we can get information about what the intrinsic properties would be if it were perfectly ordered, which gives a kind of, anchor point to thinking about the real systems. We're really terrible at solid solutions. There we are complemented by Ichiro's combi techniques. So if we found something interesting and we wanted to tweak it by doing a solid solution thing, I would not try to do that necessarily in the computer, but I would go to Ichiro or someone like Ichiro to help explore that tweaking. We're also not so good at defects. We're starting to move, actually, I'm becoming very interested in studying defect physics from first principles, especially good defects, that give you interesting functionalities. But again, these tend to expand the these are inherently not periodic, so you have to expand the supercell hugely to capture defect physics, and that is, makes you have to use bigger computers. And I do think, and I honestly do think about these as computer experiments. So we are generating data in first principles world, which is not exactly like the real world, but it's data. We could imagine this as, we can actually, the one thing I'm thinking about is structuring this really like experiments so that we would be able to use characterization tools like Raman scattering or other kinds of transport measurements and simulate those results so that we could do the experiment before the experiment. But I'm not trying to replace experiments. I got to tell, right? Everyone, that's another thing I'm always accused of. Is you want to get rid of experimentalists. And this is not true at all. This is, in the end, the only thing that matters is what happens in the lab. And what we're trying to do with first principles world is to make the time that you spend in the lab as productive and rich as possible, so that you have all the information that, like David Mandras gave you all this excellent advice yesterday about the library and the lab, and so this extends to that. The more information you go into the lab, the more likely it is that the time that you'll find something interesting when you look. That said, I also would never say don't look at something if your gut tells you to look at it, because I could be wrong, and there's the whole serendipity thing as well. So we don't want to lose that either. But again, knowledge is power, and so on. Okay, so what is in that black box that produces this magical function and the polarization and so on. So again, as as experimentalists, which again I think basically everyone is, you don't need to know too much about this, but I want to give you just a sense of the kinds of what's going on, so that when you see this information, you might know what questions to ask, know what to believe, when to be skeptical. Okay, so back to Dirac's approximate practical method. This has been realized through two theoretical advances: density functional theory, 1964, but to really get the method working required pseudo potentials, and therefore it was about in the 1980s that we first started to see real first principles calculations. So density functional theory. How many people actually know the Hohenberg-Kohn theorem? Okay, good. So you can check up on me and see if I'm making this up or not. So remember that this E naught was the ground state energy of the interacting electrons in the fixed potential due to the nuclei. And the density, the first Hohenberg theorem tells us that this energy is a variational functional of the electron density rho of r. So we're not talking wave functions, we're just talking about electron density. And if I have this functional, it has the property that when I minimize the functional with respect to rho of r, corresponding to a given number of electrons n, the minimum of that functional is the ground state energy, and the density which minimizes the functional is the ground state electron density. So if I have this functional, then I've got E naught, because I would just do the minimization for the potential of the ions fixed at r. But the catch is we don't know, the hard part here is getting the functional.
What do you use for magnetism? Do you use Kohn-Sham type of?
Yeah, we still use this approximation. So the functional has it's a total energy, and it's actually can be divided into the parts corresponding to the basic Hamiltonian, the kinetic energy of the electrons, the electron-electron interaction, and the potential energy of the electrons in the nuclear potential. At this point, approximations are needed. The first one and the biggest one has to do with the kinetic energy. So the kinetic energy is the most quantum mechanical part of this, and that was addressed by this Kohn-Sham mapping in 1965. So again, here, the technical part will be over soon, or this is the most technical part. The kinetic energy plus the electron-electron interaction, we're going to rewrite, and we're going to break this total sum down in a different way. I'm going to have the T non-int, which is the kinetic energy of a non-interacting gas, in an external potential V effective, which has has the specified ground state density rho. So two systems, one interacting, one non-interacting, have the same ground state density rho. And it's easy to find the kinetic energy in the non-interacting case. So here's some equations. This is if I have a single particle wave functions. This is now a Slater determinant, non-interacting system. I can easily write the kinetic energy, as a sum over those single particle wave functions, and then the total energy is written this way. This kinetic energy. This is explicit. This is the Hartree energy. It's just rho 1/2 integrated, and this is like a garbage can that absorbs everything else. Okay, like this is the mysterious, everything that isn't here is here. Okay, so this is still, still formally exact, and I can do then I can, when I do the variation with respect to these orbitals, I get something that looks like single particle equations in a density dependent local potential. So, and I get these eigenvalues EI. So for those of you who know Hartree-Fock, This is very, very similar in flavor to Hartree-Fock. I have a Slater determinant, which is a functional of psi's. I vary the energy with respect to the psi's to get single particle equations. And I get something that looks a lot like this, except that in Hartree-Fock, the potential is non-local. Right? It involves like some integral with the wave functions to get the exact exchange. And so this feature that the potential depends on rho is something that you see all the time when you try to describe an interacting system as an effective non-interacting system. That's the self-consistent price that you pay. Okay, so we've got this single particle. We've got it down to a single particle system and sort of pushed all the lack of knowledge into this functional EXC of rho. So I've just summarized that here. I've written this, this summarizes how EXC of rho just, basically includes everything we haven't otherwise done explicitly. And then the question is, in a practical calculation, what do we use for EXC? So the local density approximation, which a phrase you're almost certainly going to hear if you encounter first principles calculations, is that we're just going to basically take look at each point in space, look at the density there, and have a function that depends just on the local density, the density at that point, and integrate that over all space. This function is obtained from looking at Monte Carlo calculations for the interacting homogeneous electron gas, where rho is the same everywhere. So that integral just turns into a volume times that rho times this function. So you can extract this function from the homogeneous electron gas. And this goes back again to the 1970s, early 1980s. People have worked hard to try to find better approximations to this functional. There you'll see words like generalized gradient approximation, PBE, Thal, things like that. Because of our discussions yesterday about two-dimensional materials, I'll also say that there are functionals that try to do a good job on van der Waals bonding that include those features. But one common feature of these functionals is that they're not really systematically improvable. There isn't some kind of expansion where, as you go term by term, it's going to get more and more accurate. I'm sorry to say, but okay. But actually, the truth is that the local density approximation works incredibly well. And there are some reasons why that's true, like it obeys some rules exactly that we now understand. But people still use it. It's quite good. Okay, let me tell you one thing though, and I'm kind of afraid to tell you this because then you won't believe anything else that I'm going to say. But one system that I use to test my students and their understanding of density functional theory is the hydrogen atom. So I'm not expecting you to kind of work this fast. I'll just tell you the story. One electron in the field of one fixed proton. This is like the one soluble problem in quantum mechanics that we know the answer for, right? So this should be a piece of cake for our first principles method. The truth is, if I do the hydrogen atom in density functional theory, the energy is not minus 13.6, it's minus 8.1, okay, which is like pretty terrible. And the reason is that, that is the self-interaction. So I have the way that I treat exchange in the local density approximation is not exact. And therefore, I have a non-cancellation of self-interaction between the different parts, the Hartree part and the exchange part. And that leads to this disaster. But I should also say this is like the super worst case scenario for self-interaction. I mean, in a real solid, you have lots of electrons, and the importance of self-interaction, then is reduced. And even then, there are implementations of density functional theory, which is specifically address self-interaction or treat exchange more exactly, as I'll mention. Okay. So another thing you want, I guess that was in my title, like electronic structure. Band structures, so we have these eigenvalues that look like band energies. And we know that, even though solids are interacting electron systems, they behave like non-interacting systems in some ways, right? You can make band structures. You have, Landau Fermi liquid theory that gives you a theoretical foundation for why interacting systems might look like they're systems composed of non-interacting particles. So here we have some non-interacting like particles. Here we have some non-interacting like particles. We could hope that they're like the same non-interacting like particles. The truth is they're not. Okay, so again, this is another thing to be, another cautionary tale. So here's a density functional theory band structure of silicon. Your eye is drawn immediately to what's the band gap, right? The band gap here is half an EV, which we know is not the band gap of silicon. It's 1.1. Although in many other respects, this picture, if you don't look too closely, looks great. It looks like everything that we know about the band structure of silicon. So you have to be, it's easy to forget that these are, these single particle energies are not really the band structure despite the superficial resemblance. And for a lot of the time, actually, you can get away with this. You can forget that and get some useful insights into the physics of the system. But you always want to keep in the back of your mind that there might be limits to that. Also, in recent years, we know how to go beyond density functional theory to get accurate band structure. So if you're really interested in the band structure, there are first principles methods that will take you there. The hybrid functionals are sort of within DFT. They combine Hartree-Fock-like exact exchange with DFT that generally fixes up the band gaps because Hartree-Fock overestimates band gaps and local density approximation underestimates band gaps. So if you mix them together, you get good stuff, right? It pushes you in the right direction. You can more rigorously get correct band structures by doing the physics right for the excited states from the electron self-energies, and those kinds of methods are, some of those are like GW or dynamical mean field theory, but they're computationally much more intensive. And again, as time goes on, the barriers to doing those calculations goes down as computers get faster. But sometimes sometimes doing the cone-sham thing is good enough for getting a basic picture of what you're looking for. Okay, I'm keeping an eye on the time. Okay, so the other piece was pseudo potentials. And again, I just want to tell you very quickly what pseudo potentials are and what you need to know about them as experimentalists. So the problem, the reason that we needed the idea of pseudo potentials to complete the approximate method is that if you're doing total energy calculations with all electrons, you have the total energy is going to be a huge number because there's a lot of energy associated with those core electrons. But it's basically a constant. So if you're trying to make those curves that I described before, you're looking at small differences of very large numbers, which we know are hard to compute precisely. So pseudopotentials are a way of taking out that big constant energy so that you can focus on the stuff that's actually changing as you change the crystal structure and the interatomic potentials. So you separate out the valence electrons from the core electrons and look at an effective potential for the valence electrons in the, influenced by the ions, which are the core electrons in the nuclei, together with the idea that the core is essentially frozen. So this is an old picture of silicon. You would then, instead of these wiggly having these wiggly S and P functions inside the core. You would replace them by nodeless wave functions which match the real wave functions outside of the core. So away from, once you get outside of the ionic core, your wave functions match and you can do computations, everything's the same. You usually compute pseudopotentials for one atomic configuration, and then the idea is they'll transfer to other atomic configurations, like going from the atom into the solid. And there are many, many pseudopotentials out there. Yes, Daryl?
Are the pseudopotentials isotropic?
They're spherical. Well, they're like they're atomic. So all the pseudopotentials that we'll use in real calculations are atomic pseudopotentials. So they have all the symmetries of the atoms.
So they do have lobes, like they have like a p orbital would have lobes.
Oh, p orbital certainly would have lobes, but the potential in the simplest potentials, the potential that the p electron sees is spherically symmetric. So there are many pseudopotentials out there. There's a real danger that you just choose the one that gives you the answer you want, which is a terrible, terrible idea. And we do have some idea. Again, I would say that we do know that some pseudopotentials are better, just intrinsically better than others by the principles by which they're constructed. So don't fall. We try not to fall into that trap. They're also not systematically improvable. Sorry about that. And the way that we know how all this stuff works is basically by doing a lot of calculations, comparing that with experiments, and getting a sense of what kind of agreement you get and how to interpret the calculations. And again, that's a reason why if you're going to use these results, sometimes it's good to have somebody who's spends all his or her time doing it to help guide you to what you should take away from these results. Okay, and of course, you should be very careful in a pseudopotential calculation about looking at properties that depend on the wave function of the nucleus, because we just saw that they don't match. There are methods to do things like hyperfine splitting and Mossbauer with all electron, or what are called projector augmented wave potentials that correct the wave functions inside the core. All right, so here's that slide I showed you before, and now I kind of gave you a little bit better idea that we can do, that we have information about electronic band structure. Again, for time, I'm not going to talk about polarization. So if we were going to do a practical, one thing that we could do, and one thing that was a huge advance in this field, is to have open source, publicly available, professionally implemented versions of density functional theory and first principles calculations. And these are names like VASP, Abinet, Quantum Espresso, Siesta. You can go online, you can download them, you can do the tutorial, like anybody in the world can do this. And one of the reasons that I'm so happy about this compared to the old way, which was every group and every student had his or her own version, was that we can actually reproduce first principles results. So if you do this, if I'm refereeing a paper and I'm like, I'm not really sure I believe, that they did this right, I could actually reproduce that result and see for myself whether, what's going on in there. There's no barriers to its use, but you do have to be very careful. It's not that easy to do the calculations correctly, and it's even harder sometimes to interpret the results. So that's a caveat for you. So the last 5 minutes or so, I'm going to talk about what I see as this is like generation 3 of all this first principles stuff, which is that 2 years ago, when I started giving this talk a couple of years ago, I was focusing on, guiding people as to whether they should learn to use this, what they could benefit from, what they should look out for. But in fact, for many systems now, it's going to be increasingly unnecessary to do the first principles calculations yourself, because with the Materials Genome Initiative, one of the thrusts is to build databases of first principles calculations where if you want to know the band structure of something, a compound in ICSD or another crystal structure database, you don't have to learn to use the software or find someone to do it. You just go to the database and look it up, in seconds, right? Which is a great idea. So I'm going to use materials project for the example. So but I'm using samarium boron 6. So suppose you wanted to know, something about the phases of samarium boron compounds. So you could, and I'm not doing this live on the computer for 2 reasons. One, because you should never ever do that in a talk. But I also have this excuse. There was a message, when I was last night when I was kind of putting in the samarium, substituting in the samarium boron 6, that they're going to be down off and on today for maintenance. So, so I did the screenshots. Okay. So samarium boron 6, you just go to materials project. I skipped that opening page. You put in samarium and boron, say, show me the compounds. So here's the list of what's in the database, and there's the different stoichiometries and some information about the calculated versions. Like here's the band gap; they're all metallic. The energy above the hull. Okay, so we were seeing that yesterday. So like this is instant. Talk about instant gratification, right? That was another theme from yesterday. Then I could click on samarium boron 6 and look at what they provide as the computed band structure. Okay, hopefully that looks familiar. And there's a little warning here. Semi-local DFT tends to severely underestimate band gaps. You already know that. Okay. And here's a density of states. But again, you can get this in seconds. I mean, again, you should be a little careful about using it. But if you're just kind of having ideas, thinking about things, you just want to take a quick look. What's going on? This is great stuff.
So these are all compounds that are in ICSD?
Yeah. So they've done. I mean, they keep adding compounds. So as far as I know, they've essentially done this for all compounds in ICSD and other hypothetical compounds as well. So I should stress again, first principles calculations, real hypothetical doesn't matter. Also great complement to experiment, So here's some other things that might interest you. There you can take they take that computed structure and make a calculated X-ray diffraction pattern. I guess it's a powder pattern. And also they have, and I put this in for Daryl, they have some suggested substrates that would match. Again, I'm sure they're, I'm sure that, but just from a structure point of view, not from, I guess, a thermodynamics or any kind of other compatibility point of view, but just which, what compounds have planes that could match this compound. And so and here they found ones that actually seem to have very good lattice matching, very low elastic energies. Okay, so I mean, this is like, you should be very excited about this, right? And I encourage everybody can, if we were going to do a practical, in fact, I'd say let's skip the first principles calculations. Let's learn how to, access these databases and how to interpret the information that's there. And like a year from now, that's going to be even better. So, okay, so here's my, so just to wrap up, also another thing I think that you should be, very interested in is something that David Mandras mentioned yesterday, which are the studies that are coming out where people are using data filtering and machine learning on first principles data to look for certain kinds of compounds. And he mentioned this paper. And so now you can appreciate a little bit more what they say in the abstract. To say here we report some previously unknown two-dimensional materials in their electronic structure by data mining among crystal structures listed in ICSD, combined with density functional calculations. So the kind of again, the biggest limitation, and I've used ICSD for a long time to try to predict new materials, all you got in there is the structure, right? So if you are looking for a feature that's tied to something about the structure, you're in good shape. But if you're looking for any other kind of property, you're on your own. But what essentially Materials Project and similar, AFlow Lime is doing now is expanding that information, for example, by doing density functional theory calculations of the band structure. So for each entry, you have this band structure, then you have more information about the compound. Is it a metal or is it an insulator? For example, biggest question. So now they have these band structures so they can look for, certain features. And of course, if you're, this whole band structure thing is even more important for topological materials. I mean, that's where the band structure is everything. You're looking for certain features in the band structure. So these topological people have really gone to town on this too. And, so here's an example. We have, topological search for computational search for strong topological insulators. Again, I picked these very similar kinds of papers. We've examined individual electronic structures for over 60,000 materials. Okay, so they're looking for band inversion. They're looking for certain features in the computed electronic structure, which you can do through data mining, and pull out certain structure types or certain compounds that have the features you want.
Can I ask you a question about that? Do you know how many they identify? They say we identify a number of it?
I would actually say that it's probably, I have to look at the paper again because I just threw these all into my mental hopper. But usually when you identify things, it's sort of on the order of tens.
Like a handful.
It's a handful. Yeah,
not 1,000.
Usually when we do this, there's this kind of sweet spot number of things that you want, which is sort of in the order in tens. And what you do if you get 1,000, if you're so lucky as to get 1,000, usually it's the other way. Usually it's like 2 or 0. Then you just throw in some extra requirements. Like it doesn't have alkali metals in it or something. So yeah, and again, I think these. I should look and find out exactly how many, but this is this is another recent paper where again they're using this. They have a database, they have first principles calculations and group theory. We present band structure calculations and symmetry analysis. But here it's 6, okay, for 6 previously synthesized materials with Dirac nodes, that look promising. So anyway, so that's what I wanted to say. And again, I'm going to, but I really want to come back with this message. So first, I hope you're excited and intrigued about first principles calculations. There's so much, like Daryl, I could keep talking and tell you more about the work that we're doing in our group with functional materials and competing phases and things like that. But this is not the place. Actually, I get to do that on Friday, right?
We're going to talk on Friday,
yeah. So, and with that, I really want, but I also want to make sure that I think one of the things that's really important for the good of science and the good of first principles calculations is to make sure that this is a really powerful technique. No, you cannot break the apparatus by doing it wrong. Which is something that other experimentalists and Daryl at Paradigm would be worried about. But you can actually undermine the credibility of the field by doing bad work, even if you're not breaking stuff. And so also keeping myself in business, because the idea is that so I think the ideal situation is like, which I think we see in most of these papers now, is that there are theoretical collaborators who are interacting and are basically really part of the team, part of the sort of characterization step, to bring that work to the next level and make it really really deep and exciting and productive. So that's my thing. Thanks for listening.